This is video 1 of topic 8 on water quality and lakes. And you'll notice that this information is actually taken from a different textbook. We're using an environmental engineering textbook by Masters et al. From 2008. The library does have a copy of this book. The first video focuses on different characteristics of water quality. To put this information in context, roughly 10% of the world's annual runoff is withdrawn for human use each year. And this doesn't seem to be a huge amount, but consider that the supply is uneven. So first of all, some areas of the world are inundated with water, whereas others have so little rainfall that human existence is barely possible. Even areas with adequate average precipitation are vulnerable to chaotic variations from one year to the next. Unless major water storage and conveyance facilities are constructed, a region may have plenty of water on the average, but not enough to cover needs during dry spells. And so just recall from much earlier this year, the water that we use comes from three main sources: from rivers, from lakes, and from groundwater. And so there really isn't a great deal of water available on a global basis in rivers. There's somewhat more in freshwater lakes, but as we'll learn later on, that distribution is not where people are typically, and then groundwater is more available in general. And then more importantly, once water is withdrawn, used, and returned to surface waters, it's polluted in some fashion. Agricultural return water contains pesticides, fertilizers, and salts. Municipal return water contains human sewage, pharmaceuticals, and surfactants, among other things. Power plants discharge water that has a higher temperature that has environmental consequences, and industry contributes a wide range of chemical pollutants and organic wastes. Pollutants also enter water from natural sources or from human sources from non-aqueous routes. And so here we're talking about things like arsenic, antimony, and fluoride from natural mineral deposits, among many other chemicals, and mercury from the deposition from air after coal combustion, again just as examples. There's a number of interesting videos posted in a playlist on YouTube. I encourage you to watch these different ones. They focus on different types of nutrient pollution, as well as different regions of the world that face these kinds of problems.
The Cape Fear River runs down the eastern half of North Carolina, passing by major cities before emptying into the Atlantic.
This video focuses on a number of important water quality characteristics. We'll start with pathogens, we'll then move to oxygen-demanding wastes, nutrients, salts, thermal pollution, heavy metals, pesticides, volatile organic chemicals, and emerging contaminants. Contaminated water has long been known as a cause of the spread of many contagious diseases. A very early example of this connection was found by Dr. John Snow in Victorian London, UK, back in 1849. He found early evidence of a connection between human waste, drinking water, and disease. What happened was that there was a cholera outbreak in London. People were drinking from one well and became sick, while those drinking from another well did not. And so here's a version of his map where he found all of the different households that were affected by cholera. You can see they're shown here in the black little dots, and the well that they were using for their water supply was located towards the middle here. Other regions of the city that were using different drinking wells didn't have this cholera outbreak. And so when he mapped it out like this, he found that the likely source of the epidemic was the sewage that was leaking into the drinking water source from the home of a cholera patient. And so what was his solution? It was actually very simple. What he did was he removed the pump handle from the affected well, and then the cholera epidemic, at least in that neighborhood, began to recede. Now, what are pathogens? Pathogens are defined as disease-causing organisms that grow and multiply within the host. The resulting growth of microorganisms is called an infection. There's a number of different causes of these kinds of infections. We can have bacterial infections, we can have viral infections, protozoan infections, and helminths, so these are parasitic worms. You've probably heard of all of these different types of diseases. This is what schistosomiasis does. It's one of these parasitic worms. Guinea worm is even more frightful. It's called the fiery serpent in a lot of cases. And the reason is the burning sensation that afflicted people have as these worms, which can be up to 2 meters long, emerge from their feet or their ankles. Fortunately, this disease is almost eliminated. If it is successfully eradicated, it'll be only the second major disease that's been wiped out, the first being smallpox. Here's some more information about schistosomiasis. It is spread by snails, and so you can see that it passes from snails into humans, and then it passes out of humans back into snails. Schistosomiasis is a disease of poverty that leads to chronic ill health. Infection is acquired when people come into contact with fresh water that's infested with the larval forms, Cercariae, of parasitic blood flukes, which are known as schistosomes. And one of the sad things about this disease is it's often the creation of reservoirs to provide water supply that's provided the still waters that these snails need to reproduce. And so it's through efforts to improve the livelihoods of people that we've actually caused this disease to become more prevalent. Epidemics of infectious diseases emerge periodically in crowded areas with poor sanitation. These infectious diseases, at least the ones I'm highlighting here, are spread through water. And so there's a number of different classifications. We can have waterborne diseases that spread through ingestion. These are diseases like cholera or typhoid. There are water-washed diseases that are associated with a lack of water to maintain cleanliness. Here you could look at scabia or trachoma. Then we have water-based diseases that require contact with water, just simple contact, not ingestion. And so here we have schistosomiasis, for example, which spreads by mere contact with water that contains these free-swimming larvae called Cercaria. This afflicts upwards of 200 million people per year, and it kills 200,000 people per year. And as you heard on the previous slide, freshwater snails serve as the hosts and require still water, reservoirs and canals. And then we have water-related diseases that have water-dependent hosts, so things like malaria or dengue that rely on mosquitoes for transmission. The next classification is oxygen-demanding wastes. One of the most important measures of the quality of a water source is the amount of dissolved oxygen that's present in it. The saturated value in water is between 8 and 15 milligrams per liter, and it depends on the temperature and salinity level of that water. As the water is colder, it holds more oxygen. As it's warmer, it holds less. The minimum recommended level for fish is 5 milligrams per liter, but the requirements, of course, vary by the species and by the life stage of that fish. Oxygen-demanding wastes are substances that oxidize in the receiving water body and therefore use up some of the available oxygen. These are typically biodegradable organic substances. These can come from municipal or industrial wastewater sources, or actually from natural sources as well, so leaves or animal droppings in a water body or water source. And as you probably know, as the bacteria decompose the wastes, they use oxygen. And so that falling dissolved oxygen concentration threatens or even kills fish and other aquatic life. We'll come back to this topic later on in a different video. And the falling dissolved oxygen is also correlated with undesirable water tastes, odors, and colors. Nutrients are chemicals that are essential to the growth of living things. They include nitrogen, phosphorus, carbon, sulfur, calcium, potassium, iron, manganese, boron, cobalt, and others. And they're considered pollutants when concentrations are sufficient to allow the excessive growth of aquatic plants, and particularly algae. The problem is that algal blooms eventually die, and they sink to the bottom of a water body or of a lake, a stream, a pond, and then they decompose. And as they decompose, they remove dissolved oxygen from the water. The decaying algae also add color, turbidity, odors, and bad tastes to the water. We'll come back to this topic a little bit later on. We're going to talk about the process of nutrient enrichment or eutrophication. And here you can see a nice example of a set of experimental lakes where one was enriched and the other was not. This is all algae. Now, aquatic species require a long list of nutrients. The three that are most important for water quality are carbon, nitrogen, and phosphorus. In some amount, these are actually very good, right? They're nutrients. Plants need large quantities of these, and the interesting thing is the nutrient that's least available relative to the plant's needs is called the limiting nutrient. We'll come back to this later on and talk about Liebig's law of the minimum. Carbon comes from alkalinity or dissolved CO2 and decaying organic matter. It's very infrequently the limiting nutrient. Nitrogen is also not usually the limiting nutrient in fresh water, but it is frequently the limiting nutrient in seawater. Phosphorus is the opposite. Phosphorus is usually the limiting nutrient in fresh water. Nutrients introduced into water bodies come from point sources or potentially non-point sources. Point sources are commonly discharge pipes from industries, wastewater treatment plants, or waste disposal sites, mines, animal feedlots, and so on. These have been the focus of most remedial efforts over the past 30 years to address water pollution. These are, of course, easier to treat and monitor and have been, to some degree, pretty effectively treated. Non-point sources are more difficult. They're usually more intermittent and they have many entry points to streams. Here you could look at runoff from agricultural lands, pastures, ranges, small construction sites, urban areas, logging sites, and so on. These are now the largest contributor to surface water pollution in the United States and in Canada as well. Looking in a little bit more detail at the two major pollutants that I discussed a few slides ago, we have first nitrogen. And so the major sources of nitrogen are municipal wastewater discharge, runoff from animal feedlots, chemical fertilizers, and nitrogen deposition, especially near coal-fired power plants. Certain plants and bacteria can also obtain nitrogen directly from the atmosphere. These are often abundant in lakes that have high biological productivity, and this, of course, because they're fixing it from the atmosphere, makes the control of nitrogen difficult in those types of places. The key problem with nitrogen is that it contributes to eutrophication. We don't really want our surface water to be this color. It can also cause human health problems for babies in the form of blue baby syndrome. This is where nitrate in the drinking water can pose a problem, and what it does is it allows bacteria in the digestive tract of babies up to the age of 6 months to convert nitrate to nitrite. The hemoglobin in their bloodstream then is oxidized by nitrite to methemoglobin, which can't carry oxygen, and so they become blue. Phosphorus is another major nutrient that we just learned about. They're usually natural sources of nitrogen for algae and aquatic weeds, but phosphorus is generally limited in nature, and so it tends to become the controlling nutrient in rivers and lakes in freshwater. Human activities often provide enough phosphorus to allow the excessive growth of algae and aquatic weeds. Then it looks like this. The sources can be agricultural runoff, animal feedlot discharges, domestic sewage, feces, and detergents. Detergents commonly now contain, I believe, no phosphate as of the last decade or so, and so it comes from other sources typically. Phosphorus-induced eutrophication is now the largest water quality problem in lakes, reservoirs, and ponds. As mentioned before, most of the phosphorus is from non-point sources, and one of the biggest problems with phosphorus is that it tends to stay in soil once it's introduced. And so the addition of phosphorus to agricultural land will be accumulated in the soils, and it's still applied in excess, so even if we stop applying fertilizers so much, it'll continue to wash out of the soils for years to come and cause water quality problems. Here's a nice map of water quality in the Canadian prairies. This is from Environment Canada about 10 years ago. You can see here, this is phosphorus on this side and nitrogen on this side of each of these pies. You can see increasing trends in the solid colors. or no trends in blue, and then decreasing trends are shown in green. And then you'll notice there's also a little dot, a little circle here within the pie. This shows the trophic status, which we'll come back to in a later video. Oligotrophic are the very clear waters. Hypereutrophic are the very murky pea green waters. And so you can see as we go from the headwaters towards Lake Winnipeg and then ultimately Hudson's Bay, the water goes from being very clean, very clear, ultra-oligotrophic, to being hypereutrophic as we get towards Lake Winnipeg. An interesting thing is that the water quality has not changed between 2002 and 2018 at the majority of sites across southern Canada. Okay, so this is still a fairly accurate map. Salts are also important. Water can accumulate a variety of dissolved solids, or salts, as it passes through soils and rocks to the ocean. Cations include sodium, calcium, magnesium, and potassium. Anions include chloride, sulfate, and bicarbonate, and many others. We can analyze water for concentrations of each cation and anion, but a much simpler, more commonly used measure of salinity is just the total dissolved solids, or TDS. Fresh water is classified as having a TDS of less than about 1,500 milligrams per liter. People drink water that has less than about 500 milligrams per liter. Brackish water, which is salty but not ocean salty, has total dissolved solids up to about 5,000 milligrams per liter. And saline water, in other words ocean water, has TDS values above 5,000 and really about 30,000 to 34,000 milligrams per liter. TDS concentration is an indicator of the usefulness of water for various different purposes. Drinking water, as I said, has a maximum TDS of about 500. Livestock can tolerate more. So poultry can tolerate almost 3,000, and cattle can drink brackish water. They can get up to 1/3 of seawater, 10,000 milligrams per liter. Agriculture must manage irrigation water carefully if it's above about 500 milligrams per liter. And so if you have enough drainage, you can permit TDS of up to about 1,500, but above 2,100, the water becomes unsuitable. And there's a good reason for that. Irrigated agriculture, especially in arid areas, is vulnerable to the accumulation of salts in the soil because of evapotranspiration on cropland and from the increased evaporation from reservoirs that then concentrates the salts that are applied to agricultural fields. Importantly, roughly 1/3 of western United States irrigated lands have a salt problem. It's estimated that 100,000 tons of salt are imported annually in southern Arizona through the consumption of fresh water, the Colorado River. And there are theories that the collapse of ancient civilizations in the Fertile Crescent in the Middle East are related to this salinization of irrigated agriculture. This looks like snow here. These are sugar beets, but it's actually salt crusts on the soils that are used for growing these beets. This is a drip irrigation system, and so you can see very clearly where the holes are in this pipe for dripping water onto this corn crop. Salt accumulation in soils can be controlled by flushing those salts away. Doing this requires additional irrigation water, so that increases the costs, as well as wasting water itself. More seriously, it can raise the water table. So the water table can come quite close to the surface of the soil, and it can then drown the crops. Their roots are always wet. Salt removal can also have environmental effects. So fertilizers and pesticides will be washed out. That can affect natural ecosystems. There are lots of examples of this kind of problem. A wetland in Florida, for example, was poisoned by selenium from an irrigated field as the salt and pesticides and various other things were washed out to reduce salt accumulation. Thermal pollution is another problem. Large electricity plants use very large amounts of water for cooling. And so, as an example, you can get up to 90 to 180 cubic meters of water required per megawatt hour, or in other words, these plants can pass through their cooling systems 150,000 cubic meters of water per hour. This can often warm the water in the river by 10 degrees Celsius or more. Some species will benefit from this, others are harmed. One of the big problems happens, though, when the plant is closed down for periodic maintenance and the flow stops, which cools the water, and then you can have lots of dead fish. Higher water temperatures also permit more evaporation from the surface water, and they can raise the metabolic rates. So a 2 times increase in metabolic rate for a 10 degrees Celsius rise. And as we learned earlier, colder water holds more oxygen, so warmer water decreases the DO levels. Heavy metals can also be present in water. From a chemical perspective, a metal is an element that will give up one or more electrons to form a cation in aqueous solution. This is, of course, an imprecise definition, as some elements exhibit metallic and non-metallic characteristics, and they'll form anions in solution. These are called the metalloids, so things like selenium, arsenic, phosphorus, silicon, and boron. A heavy metal is usually used to refer to a metal with a specific gravity that's 4 to 5 times greater than water. The most important ones that we're worried about in water are mercury, lead, cadmium, and arsenic. They look like this. The biggest problem is that most of these metals are toxic. So aluminum, arsenic, beryllium, bismuth, cadmium, chromium, they're often essential nutrients in our diets, but they're dangerous at high doses. Others, however, are just toxic at any level, and they can cause a range of problems. From a water quality perspective, the big problem here is that metals are totally non-degradable. They're virtually indestructible in the environment, and so once they're in the sediments, for example, in a river, they can be washed into the river again. And so when they're remediated in the environment, we have to get out those sediments and dispose of them in a permanent fashion. Another class of water pollutants are pesticides, volatile organic chemicals, and others. Pesticides are chemicals that kill organisms that humans consider undesirable. We use insecticides, herbicides, rodenticides, and fungicides, for example. The problem is that these chemicals are often persistent and they're soluble in hydrocarbon solvents, and so then they can bioaccumulate, like DDT, which you've probably heard of. Volatile organic chemicals, or VOCs, are commonly found in groundwater. These are often used as solvents in industry. Some are known or suspected carcinogens or mutagens, and some common examples that you may have heard of include vinyl chloride, trichloroethylene, tetrachloroethylene, and so on. We'll talk more about these actually in the groundwater unit later in the course. There are also a class of emerging contaminants that have been identified as of special interest since the 1990s. These include endocrine disruptors or antibiotic-resistant pathogens. The relative importance of these different pollutants depends on the water body in question. And so in the United States, states are required to submit water quality assessments of their rivers, lakes, and estuaries as part of their Clean Water Act. In Canada, the provinces have their own water quality guidelines and must also meet requirements from the Department of Fisheries and Oceans, Environment Canada or Environment and Climate Change Canada, Health Canada, and so on. Assessments are intended to identify sources of pollution and the fraction of the resource that's impaired, quote unquote, by pollutants. What they mean by this term is a water body is called impaired when a designated beneficial use, which might be aquatic life support or fish consumption or recreation, is no longer supported by the quality of water. This figure here shows the fraction of impaired river and stream miles in the United States, broken down by, first of all, the pollutant or the stressor, and secondly, by the source of the pollution. And so here you can see in rivers and streams, the biggest problem is pathogens, followed by siltation, followed by habitat alterations, oxygen depleting substances, nutrients, thermal modifications, metals, and flow alterations. And then in terms of the source, it's primarily agriculture, but also hydrological modifications, habitat modifications, and urban runoff, and so on. So as you saw in the previous slide, in rivers, the most common problems are pathogens and siltation. The pathogens come from sewage, wildlife fecal matter, runoff from farms and feedlots, and the silt comes from solids that are washed off plowed fields, logging sites, urban areas, and stream banks by rain. And the problem with the silt is that the sediment load can smother fish habitat and aquatic plants and so on. For lakes and reservoirs, which are in this figure, the biggest problems are nutrients and metals, followed by siltation, TDS, oxygen-depleting substances, algal growth, and pesticides. And again, the primary source is agriculture, followed by modifications to the rivers and lakes, followed by urban runoff and storm sewers, and then non-point sources and so on. Now, that set of graphs was from an older study from 2002 conducted by the US EPA. The interesting thing is the title here is Recent Changes in Water Quality. There actually aren't really any changes in the past 20 years. And so here's a recent study on water quality trends in US rivers over 10 years from 2002 to 2012, published in 2019. So they looked at water quality trends for ammonia, chloride, nitrate, sulfate, TDS, total nitrogen, and total phosphorus at 762 sites in the coterminous United States. And what they found was very interesting, which was that water quality conditions are not substantially improving in the United States, but nor are they degrading. In previous courses, I'm sure you've heard about an important measure of water quality called BOD, or biochemical oxygen demand. You know by now from this video content that surface water is highly susceptible to contamination and was historically the most convenient sewer for industries and municipalities. And so then oxygen demanding wastes are a pervasive category of surface water pollutant that affect both still and moving water and deserving of special attention. The mechanism is that biodegradable waste is released into surface water and is then fed on by microorganisms, especially bacteria. They break wastes into simpler organic and inorganic substances. In aerobic conditions, this isn't really a big problem. The decomposition produces typically unobjectionable, stable end products like CO2, sulfate, orthophosphate, and nitrate. So, not perfect, but not a big deal. However, in anaerobic conditions, we have a different set of microorganisms that decompose wastes. They produce end products that can be highly objectionable, including hydrogen sulfide, which can kill you, ammonia, and methane. And so then we have this measure. The amount of oxygen that's required by microorganisms to oxidize organic wastes aerobically is called, again, the biochemical oxygen demand. This is usually measured in milligrams of oxygen that are required per liter of wastewater, in other words, milligrams per liter. BOD is made up of two parts. First of all, we have carbonaceous oxygen demand, or CBOD, and secondly, we have nitrogenous oxygen demand, or NBOD. We're going to ignore this distinction in this class, and we're going to focus on a common BOD test, which is the 5-day BOD. Now, we could actually consider the amount of oxygen that's required to completely degrade a sample, but such a test would take quite a long time. It would be too long to be practical. And so 5 days has just become the standard practice. There's nothing magical about 5 days, it's just the standard practice. It does mean that the NBOD has not typically started yet, so it's just the CBOD component. The 5-day BOD is the total amount of oxygen that's consumed by microorganisms in the first 5 days of biodegradation. The simplest form of a 5-day BOD test would be putting a sample into a stoppered bottle and then measuring the concentration of the DO at the very beginning of the test and then 5 days later. The difference divided by the volume of the sample would give me a 5-day BOD. To conduct this test, I have to make sure that no light can reach my sample, because algae can actually add dissolved oxygen through photosynthesis. The bottle has to be sealed to prevent air from replenishing any DO, and we use a standard temperature of 20 degrees Celsius. The oxygen demand of typical waste is several hundred milligrams per liter, but the saturated DO of water at 20 degrees Celsius is only 9.1 milligrams per liter, and so we often use sample dilution to keep the final dissolved oxygen after 5 days greater than 0. Because, of course, if the DO drops to 0 during a 5-day test, the test is useless. Here's the equation we use. I'm going to leave the rest of the notes for you to go through. I assume that you have learned about BOD in previous courses, and so please go through the remainder. We'll do a few examples as well in the synchronous sessions. This is the end of video 1.